back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And today we're going to try to answer a few questions about, well, what's out there? I mean, what's out there in outer space? Are there alien civilizations? If so, what would it be like to make contact with one of them? With us today is a professor of astrophysics, Professor Adam Frank. He's a professor at the University of Rochester. Also, he's a commentator on NPR All Things Considered, and he was also a science consultant for Marvel Studios' Doctor Strange. And he's the author of an exciting new book called The Light of the Stars, okay? Alien Worlds and the Fate of the Earth. So today we're going to talk not just about extrasolar planets, but civilizations that may or may not thrive or fall on some of these extrasolar planets in outer space. We're not going to talk about little green men. We're going to talk to an astrophysicist, Professor Adam Frank, professor of astrophysics at the University of Rochester, author of a new book, The Light of the Stars, Alien Worlds and the Fate of the Earth. Well, Adam, first question for you that we always ask our guests is, how did you as a youth first get interested in science? What set you off on this great journey?
Well, remarkably, it was my father's pulp science fiction books. He, as a 5-year-old, I remember wandering around in his library and pulling out those old amazing science magazines. And on the covers, they had these great pictures or paintings of guys bouncing around on the moon or rocket ships, blasting off of alien planets. And that was it. I was 5 years old, and that got me started. And I haven't, the passion has never cooled since then.
Okay, well, let's just jump right into what's happening in outer space and in the laboratories. First of all, let's talk about Kepler, a satellite that has forced astronomers to rewrite every high school textbook that is taught in the United States and the world. First of all, 4,000 planets have now been identified orbiting other stars. First of all, tell us how we do it. How do we know the existence of these 4,000 planets? And do any of them resemble the planet Earth?
Well, it's really amazing how rapidly this progress has been made. When I started as a young astronomer, we didn't know whether there were any planets anywhere. And in fact, that question goes back 3,000 years to the Greeks. And in just the last 20 years or so, we've discovered that pretty much what we can extrapolate from that data is that every star in the sky has planets going around it. And with Kepler, what we do is we look for that when the planet passes in front of the star, there's a small diminution. The light from the star gets blocked a little bit. It's a little like eclipse. We call it a transit. And during that moment, we can get enough characteristics of the planet to know that it's there, to know its size, to know something about its orbit. So it's, Kepler allowed us, there's other ways to find planets, but Kepler allowed us to do planet hunting wholesale, rather than retail, which was the way of doing it beforehand. So, basically it was through that transit, seeing the transits of planets in front of their stars that we were able to see many, as you said, thousands of planets. And from that, we're now able to extrapolate the fact that pretty much almost every star in the sky, we believe, has planets orbiting it.
So let's do a census of the Milky Way galaxy. Assuming that there are roughly 100 billion or so stars in the Milky Way galaxy, are you telling me that there could be 100 billion planets at a minimum that exist in our own backyard, the Milky Way galaxy? Is that what you're saying?
Absolutely. That's pretty much what we found. Other than the most massive stars, which are pretty rare, the extrapolating from the Kepler data, we can say that almost all the stars in the galaxy have at least one. And what we've also found, you asked the question about Earth, we found that 1 out of every 5 of those stars has a planet that's in the right place, what we call the habitable zone or the Goldilocks zone. It's in the right place for life to form, meaning that liquid water could exist on its surface.
So, in other words, you're talking about billions of planets out there that resemble the Earth. Is that what you're saying?
Well, at least are in the right place. When we talk about, it doesn't necessarily have to resemble the Earth in terms of size, etc. What we are really interested in is the ability to have liquid water on its surface. That's what we think about. This goes back all the way to the early 1960s, people thinking about what they call the Goldilocks zone. And yes, billions and billions of planets are in the right place, are Earth-like enough in terms of this question of liquid water on the surface, that yes, that's the kind of planet where we think life has the possibility of starting.
Now, the Kepler satellite, unfortunately, right now is crippled. However, the TESS satellite is up there, and that may even give us even more Earth-like planets being discovered in space, right?
Absolutely. The TESS is sort of the next step after Kepler in terms of what it's going to be looking for. It's looking at a larger portion of the sky. It's going to be looking for specifically a little bit more for Earth-like bodies, Earth-like planets, because it's going to be looking at the brighter stars in the sky, which means sort of, most stars, remarkably, most stars in the sky are not like the sun. The sun is not an average star. Most are much smaller than the sun. But what TESS is going to be looking at is much more sun-like stars where we're going to have a better chance of finding Earth-like planets around them. So this is just the beginning. We are set over the next, people have to understand, over the next 30 years, 50 years, 100 years, we are going to be staring at all these planets we've discovered in detail with the ability perhaps to see the characteristics of life through seeing their atmosphere.
Now, the Webb Space Telescope, the replacement for the Hubble Space Telescope, is going to go up into outer space, and some people hope that it might give us pictures of some of these planets and perhaps a glimpse into their atmospheres. Could you elaborate?
Yes, the most important transition that's happened, and this is the thing I really want people to understand, is that we are really in a fundamentally new era in thinking about life and the universe. Beforehand, we had radio telescopes that we pointed at planets or at stars and hoped maybe someone was sending us a signal. But now, because we've discovered all these planets and we have the ability to stare at these planets over and over again, every time we turn the telescope in that direction, what we have the chance of doing is actually catching, as I said, transit is when the planet passes in front of the star, and there's a moment.
Okay, Adam, we're going to have to take a short commercial break, but after that, we're going to get right to you, and we're going to talk about civilizations, extraterrestrial civilizations out there. In other words, aliens in outer space. Science Fantastic with Professor Michio Kaku. In this hour, we have with us a professor of astrophysics, Professor Adam Frank of the University of Rochester, author of a new book, The Light of the Stars, Alien Worlds, and the Fate of the Earth. So today, we're just not going to talk about planets in outer space. We're going to talk about potential civilizations out there, some of which may be even more advanced than our civilization. Well, before the break, we were talking about the fact that we had the Kepler satellite giving us gorgeous information about 4,000 planets, many of them the size of Jupiter, orbiting other stars. A new satellite called TESS, which will give us an even better look at Earth-sized planets, and a new telescope, an infrared telescope, the replacement for the Hubble, which is going to go up into outer space, which may eventually even give us photographs of some of these planets. So with all this information pouring in, people are now re-examining all the old assumptions that we made back in the 1950s, including the Drake equation. So tell us a little bit about the Drake equation.
Well, the Drake equation was basically a way of answering the question, how many civilizations are there out there now? And the brilliance of what Drake did is he broke that question up into 7 different individual factors, each of one of which is a problem you could study. Things like how many planets there are around each star, whether or not you get life around any of those planets, on any of those planets, etc.
Yes, and what number did he come up with? I mean, that's the key question, right? And also Carl Sagan, he redid the Drake equation. He came up with his numbers, too. So how many alien civilizations are there in our own backyard, the Milky Way galaxy?
Well, the problem problem is, those factors, up until recently, most of those factors you were just guessing at, and so either you were an optimist or a pessimist about it, and so there really was no hard limit. Recently, my colleague and I used all that Kepler data, and what we were able to do was get the first empirical limit on the probability for civilizations out there. And what we found was that unless the probability per planet was less than 1 in 10 billion trillion, then we were not the first time a civilization has occurred. So that's the only truly scientific thing you can say. But what it says is that unless the universe is really biased against it, unless the laws of physics and chemistry are really biased against it, then we're not the first time there's been a civilization.
Now, I understand that back in the 50s, when people did the calculation, they came up with numbers like in the tens of thousands. Carl Sagan then redid the calculation and came up with perhaps millions of civilizations, in which case some of them would be rather close to us. But other people since then have reduced the numbers considerably. So tell us a little about the back and forth and why there is so much uncertainty with regards to the Drake equation.
Well, the problem is that a lot of that, well, here's the interesting thing. So when Drake wrote down his equation, there's 7 factors in it. We only knew one, which was the number of stars in the Milky Way. But now we've nailed 2 more of them, the number of planets in the habitable zone and the fraction of stars with planets. But all the other terms, like the fraction of planets that develop life, we just don't have any good science right now to constrain that. So that, or one of the other terms is the fraction of intelligent planet life that becomes intelligence. So that requires knowing something about evolution, and we just don't have the guide, the physics and chemistry and biology guide to answer that question for other worlds. So that's why there's so much uncertainty about the actual number.
Okay, well, let's do some numbers. First of all, we have 100 billion stars in the Milky Way galaxy. And the Hubble Space Telescope, there are about 100 billion galaxies that we can see in the visible universe. So the total number we get is 100 billion times 100 billion, which is an astronomical number. However, other people say that the probability of life getting off the ground, intelligent life, is so tiny that perhaps the number could be 0. So what are your thoughts about the optimistic and the pessimists who use the Drake equation to put forth their philosophy?
Well, that's what we did in that paper with Woody Sullivan. What we showed is that unless those probabilities all work out to be less than 1 in 10 billion trillion, for us to be the only one, then it's happened before. What we were basically showing was that even if you look at the literature that people have argued about it, even the most pessimist of pessimists pretty much was an optimist based on what we now know about how many planets there are. So we showed that unless nature was so biased against civilizations, that the number was, the per planet probability was 1 in 10 billion trillion, then as long as it was anywhere above that, life and civilization has happened before. So I think one thing we can see is that you have to be a really, really serious pessimist now, a hyper pessimist, to think that there's never been a civilization before in cosmic history.
Okay, well, there are a lot of party poopers out there. One set of pessimists say that you need a large moon to stabilize the Earth's orbit, otherwise the Earth would tumble, and most planets do not have large moons, and so they will tumble, and therefore they will not have any life on them. Other people say that the dinosaurs were around for 200 million years. They never became intelligent. Lifespan on the Earth for 3.5 billion years. Not a single life form became intelligent until a blink of an eye, and here we are, you and me, talking about these things. So some people say that when you reanalyze the terms in the Drake equation, the more we learn that life is really quite precious and extremely difficult to get off the ground. But what are your thoughts?
Well, I think that, the problem again is that all of those kinds of arguments sort of rely on extrapolating what has happened here into the universe. And I just don't think, that the universe has had so many opportunities in terms of planets to run these experiments over and over again. I think that the universe is going to be much more fecund than those pessimists give the universe credit for. Really, again, we have 10 billion trillion habitable zone planets in the universe. That's a lot of experiments for the nature to run.
Well, recently I've heard some astrophysicists say that microbial life could indeed be rather common throughout the universe for precisely those reasons that you mentioned. But how many of these microbes will become intelligent? And that's where they say that's a limiting factor. What are your thoughts?
Well, there is, yes. There's this thing called the hard step model where people say, like, look, it's easy to get microbes, but in order to get all the way up to a civilization, there has to be these very particular things like the evolution of oxygen creating photosynthesis, for example, that are very hard and very rare, and there's a number of these steps. But if you actually do the math, you can actually work through those pessimist math, and you still end up with potentially trillions of worlds out there across the universe, not just the galaxy, but the universe that have had a civilization. Now, what we don't know is how long they last, right? It could be that every civilization only lasts 200 years, and so, no one's around now because no one lasts very long.
That's a comforting thought, isn't it? Well... Okay, then we go to the Fermi paradox. Enrico Fermi, Nobel Prize winner, one of the founders of atomic physics, asked the embarrassing question, well, if life is so abundant throughout the universe, then where are they? I mean, why don't they visit us? Why don't they land on the White House lawn, for God's sake, and announce their existence? So what are your thoughts about the question, where are they?
Right. That is a great question. And there's two pieces. People sort of do two things with this. One is they say, look, we've never heard anything from anybody. And that part I don't agree with because we really haven't looked very much. Like SETI, it's not like everybody's out there doing SETI all the time. There's never been a well-funded SETI project. So we barely looked. Like if the ocean is what we're searching, basically right now we've looked for a thimble full of water. So in that respect, I don't think the Fermi paradox is a paradox. But you can work out the math about colonization. If there was just one civilization that started colonizing the galaxy, yeah, they should have swept by now. So that is more of a problem. But here's the question. What if they landed here 1 billion years ago, and they only lasted 1 million years as a civilization, right? Every civilization is going to have a finite lifetime. Would we even know that they were here? So that is also a potential solution to it. It depends on when they came.
Well, privately, if you remove your astrophysicist hat and put on your human hat, when you watch the movies and you see all these aliens come at you every summertime, then the question is, well, what are your personal thoughts about why they don't visit us?
Yeah, that's a really good question. And I love science fiction. I try and watch almost everything. I know you're really great about including great science fiction ideas as a springboard for in your own work. And that's something I think about a lot in this work. And if I had to guess, I mean, when I think about it, first of all, I don't think we're that interesting, right? I'd like to believe that the galaxy may be teeming with civilizations, and we're just not a very interesting place to visit. So that's why we're not constantly being buzzed by. So that's my personal hope. I also think, though, that, it may, putting a little bit of my science fiction hat on, I think it may be that interstellar travel may be very, very difficult, both very expensive and very difficult. And so we kind of, we love the idea of warp drives and everything, but maybe there is no such thing as a warp drive. We'd like to believe it, but, maybe it just travel between the stars takes a long, if you don't have a warp drive, it's going to take you tens, hundreds, maybe thousands of years to get between one star and another. And maybe that's just so difficult that nobody wants to do it. But finally, we might add, maybe everybody becomes silicon. Another possibility is that it's robots really that is the next phase, and robots may have a very different set of interests about the universe than biological beings do.
Well, another possibility is, mentioned in the movie 2001, where there's a probe on the moon lift over from a passing galactic civilization. In principle, these probes are self-replicating, like a virus. They land on the moon, make copies of themselves, and launch off to other planets, like in the movie. And perhaps that's the way that a civilization can colonize the entire galaxy in a few 100,000 years at sub-light speed. So what are your thoughts about, like a virus, a self-replicating robot that could make copies of itself, simply seeding the galaxy, sending information back to the home planet, and that would be the cheapest way to explore the galaxy without having Captain Kirk go from star system to star system, which is very inefficient.
Yeah, and that's, there's a number of science fiction ideas that sort of have that idea that a civilization either, completely stops being biological and then just becomes sort of interstellar, traveling, self-replicating robots, or, they stay at home and they use their robots to be, the problem with that is that you need a very long-lived civilization for that to be. Like, if you're going to stay at home and you're just going to send robots off, then basically, you need to be around for hundreds of thousands or millions of years in order for that to be a good way to explore the universe. But I absolutely think that it is very possible that the era of being biological may be relatively short, that most civilizations, perhaps after a million years or so, basically give up on being biological, or they invent artificial intelligence, which then takes over. But those are, I think, I can see those as being real possibilities.
Yeah, I think so. Maybe one day we'll simply merge with our creations. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Adam Frank, Professor of Astrophysics at the University of Rochester, author of a new book, The Light of the Stars, Alien Worlds and the Fate of the Earth. Well, in your book, you also mentioned the Kardashev scale of advanced civilizations. So give us a quick summary of at least one attempt to catalog civilizations that may be thousands of years more advanced than ours.
Yeah, so Kardashev was a Russian physicist, sort of Carl Sagan's Russian analog. And what happened with that, what he proposed was that civilizations would naturally go through three stages of advancement, which he scaled by how much energy they use. And the first, the Kardashev Type 1 planet, or civilization, would be a civilization that used all the energy, most of that means sunlight, falling on their planet. A Type 2 civilization would be able to harvest all the energy coming from their star. So they would build like a giant, what we call a Dyson sphere, around their entire star and capture all of its energy. And then a Type 3 civilization would be one that could capture all the energy coming from all the billions of stars in the galaxy. So they would be like gods to us. I mean, actually, Type 2 would be like gods to us as well. So that was the basic idea of the Kardashev scale.
Okay, now we've looked for Kardashev Type 2 stars. They would emit infrared radiation, and we've scanned the heavens looking for the signature of a Type 2 civilization, and we find none. However, we were able to get a lower limit, so at least we can put numbers and boundaries on the probability of finding it. But isn't that rather kind of pessimistic? That is, we look for these advanced civilizations. It's very hard to disguise yourself because if you create heat will be seen throughout the universe. So isn't it rather pessimistic that we've looked for them, but we haven't found any? Or maybe we haven't looked hard enough.
Well, it also assumes that it assumes that Kardashev's idea was correct, right? That is the way that it progressed. Like one way, so I in my papers and in the book, I sort of point out a big flaw in the Kardashev Type 1 idea, which was solely based on energy, and it forgets to acknowledge that your civilization is growing up on a planet with a biosphere, and you can't just bring a biosphere to heal. You can't just use as much energy as you want and not expect something to happen. That's the great lesson of climate change and the Anthropocene. So, as I like to call it, the Kardashev Type 1 is a kind of planetary brutalism, because it sort of thinks that you can just you can turn your planet into something like Trantor, the homeworld of the Foundation series empire, where the planet is underneath a giant city that goes 300 levels. So I think there may be ways in which the Kardashev scale fails to take into account what you have to do to progress through these levels. Certainly for a Type 1, it missed what you have to do to progress through those levels. So maybe that's a way that the basic idea was right, but there may be subtleties that need to be considered.
Well, one possible amendment to the Kardashev scale is looking at information. That's what Carl Sagan said. Instead of simply populating more and more energy factories, which will emit heat and eventually heat up your planet by the second law of thermodynamics, you use computers. And computers can can do things much more efficiently, so you can have a gigantic galactic civilization without consuming so much energy because you have microchips and miniaturization of this. So what are your thoughts about getting around the problem of thermodynamics by using information?
Well, I certainly think on a planetary scale, when a civilization is young and you haven't invented, miraculous technologies or what technologies that seem miraculous to us, you're going to be stuck with thermodynamics, and that's what a lot of my research has been. But as you point out, as we climb the technological advancement, it may be the idea that we're going to be directly using energy, like we're getting, like Newton's laws to move ourselves around or to build the civilization, the working parts of our civilization. That may be, outdated. And as we talked about before, it may be that, silicon or a machine, information processing machines become really what we're thinking about when we think about civilization. So yes, it's a very 1950s idea that the advanced civilizations are giant rocket ships propagating from one place to the other using chemical propellants or whatever.
Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Adam Frank, Professor of Astrophysics at the University of Rochester, author of a new book, The Light of the Stars, Alien Worlds and the Fate of the Earth. Well, when we last left off, we were talking about the Kardashev scale, but you have your own scale. It's class 1 through 5. So explain to us your classification of planets.
Well, the thing we were interested in this paper, which is also part of the book, was what happens, what does a civilization that has reached sustainability look like, right? So this is the great challenge for our civilization right now. How do we build a sustainable form of human civilization that doesn't push the planet off into crazy climate states that make it hard for a civilization to exist? So what we did is we looked at all the planets we know about, and we tried to extrapolate from that, or at least, articulate that what a planet with a long-term, and we're talking millions of years, long civilization, what would that have to look like? Because as we said, the Kardashev scale is kind of brutal. It just thinks you can do anything you want if you have enough energy, but we know that's not true for biosphere. So class 1 was a planet with no atmosphere. Class 2 was a planet like Mars that has an atmosphere but no life. Class 3 was like the early Earth, when you had life, but it hadn't really kind of taken over. Class 4 was Earth before us. A vibrant biosphere where the biosphere really dominates the way the planet works. And then class 5 would be a planet with a long-term energy-intensive civilization, and somehow the biosphere and the civilization have come into some kind of equilibrium with each other.
Yeah, when I saw that, I thought, well, that's nice, but class 5 which is going to be most interesting, doesn't give you a blueprint for the future. The Kardashev scale actually takes you out a few 100,000 years. We can debate whether or not it's brutal, but your classification, I think, needs more detail about what a class 5 planet is. Could you elaborate?
Well, yes, I think that's absolutely true. What we were first proposing, the main idea of that paper, and now we're working on other papers about this, was the idea that a planet with a long-term civilization on it, energy-intensive civilization, would have specific characteristics. And that's what we should be shooting for. So first, you identify the fact that there's going to be certain things that are different about a planet with a long-term civilization on it than a planet without it, and then you can begin to articulate what those characteristics are. For example, in the paper, we suggested that there would be more dissipation, more power, more entropy being generated on a planet with a long-term civilization than one without. Because you can actually see the ramp up. If you look at classes 1 to class 4 planets we know about, you can see that there's more and more energy being dissipated, basically, energy being used to do work on those 4. So we hypothesized that on a class 5 planet, there would be far more energy being used to do work on a planet like that.
Well, then don't you bump up against the second law of thermodynamics? A lot of waste heat will be generated, and eventually your planet will be incinerated. So what are your thoughts about waste heat? How do you get rid of all that heat from your engines?
Yeah, the interesting thing about this is the way the biosphere actually, that's why it has to be a collaborative relationship with the biosphere. That's, I think, what Kardashev missed. Because, the biosphere is very inventive about getting around heat engines, getting around the second law of thermodynamics, minimizing things. Like photosynthesis was the most brilliant example of being able to find a way to reduce your entropy. So in that case, it was by directly tapping energy from sunlight. So by developing a cooperative relationship with the biosphere, you can channel that energy in ways that minimizes the thermodynamic impact. That's our idea, that it would be you and the biosphere working to ways to innovate for evolutionary innovation to be able to handle that question.
Well, actually, of all people, the richest man in the world, Jeff Bezos of Amazon, has actually come up with a way to get around this problem. He advocates that we put all our heavy machinery in outer space and make Earth into a garden. So Earth would be a celestial park with all the heavy industry in outer space, in which case all the heat generation, because of all the factories, would be done in outer space, leaving the Earth to become this garden. What are your thoughts? Because after all, he's already created a spaceport in Texas, and he has a fleet of rockets to back it up, the richest man on Earth.
I think that's a great idea. I mean, it's very, sort of long-term. I mean, but maybe long-term, maybe only in the case of centuries, but I agree with that. I mean, I think that humanity's future is the solar system, right? That the stars may be very far away. They may be fruit that's hard to get, but the solar system, as watchers of The Expanse, hopefully everybody watches the show The Expanse, know is that the solar system is really where the next couple of, I think, the next few centuries of human history is going to be played out. And yes, I agree with that.
Okay.
That we should try and do exactly that.
Okay, Adam, unfortunately we have run out of time, but thank you so much for being on Science Fantastic.
It was a great pleasure. Thank you.